In sections 3 and 4 of Chapter 7 in the ECU 301 workbook will concern voltage in terms of current for capacitance, as well as the storage energy in a capacitance. So at the bottom here we are at the bottom of page 83 and starting at section 7.3, we're going to look at voltage in terms of current. So the question is, how do we get the charge and the voltage on a capacitance if you actually knew the current flowing through them? Keeping in mind, of course, current is the capacitance, the constant C times dV/dt, the derivative or the rate of change of the velocity. So if we just use the fundamental theorem of calculus, then the charge you would get by integrating the current, all right? And so what you would get is indicated here in this formula that the charge then from the current would be the integral from t0 to t of I of t dt plus the initial charge at time 0. Again, that would be represented by the Q of t sub 0. Keep in mind, we know now that in terms of the charge function is always C times V of t. Therefore, we can write V of t simply as whatever the charge function is divided by 1 over C. So we're just going to take this integral formula and just multiply by 1 over capital C, where that is the capacitance constant or the constant proportionality between the charge and the voltage for capacitance. Since the initial voltage would then be Q of T0 divided by the capacitance constant C, eventually what we can write is this formula here at the bottom, that the voltage is simply 1 over the capacitance proportionality constant times that integral plus the initial voltage. So it's all represented in terms of voltage there. So that's a nice way we can get voltage then. If we have current, we just simply need to integrate to get the voltage across a capacitance. Now flipping over to page 84, we'll do an example. Typically T0 is usually started at time 0 for most problems, but it doesn't have to be. But what we're going to do is look at this capacitance and determine the voltage for the capacitance. And then what we're going to do is plot the current, the charge, and the voltage to scale versus time, so we can see the differences in the shapes of all these curves, all right? So initially, again, what we have here is we certainly can see we have a 0.1 microfarad capacitance, and we have a current function, which is sinusoidal, changes in sign and magnitude. And the polarity is indicated here correctly in terms of PRC for the capacitance, all right? So after the initial time, so after, let's say, t equals t0, which is the initial time 0, we would have, in terms of the current, I of t would be 0.5 times sine of 10 to the 4th t, and this is, of course, in radian measure. It's always in radians, okay? So if suppose we had an initial charge of 0, so let's just suppose for this capacitance, initially we have no charge on it. That's how we would represent that initial condition. There's absolutely no charge to start with. Then the charge function that would be produced by our definition, because we have the current, is we would integrate from time 0 to t. Again, we're taking t0 to be actually time 0. And then we would integrate our current function and then add the initial charge, which we've assumed is initially 0, right? So for this particular problem, what we would have is the integral from 0 to t of 0.5 times the sine of 10 to the 4th t, and then dt, and should have written dt there, okay, with respect to time, plus 0. And of course, that is just a simple integral now that we should be able to do. The constant comes out, the 0.5. The integral of sine is negative cosine, so we should have minus 0.5, and we'll have times 10 to the minus 4 cosine of 10 to the 4th t evaluated at 0 and t. So I'm just doing a very simple integral there. The integral of sine u du is minus cosine u du, all right? So just using our standard trigonometric integrals there, all right? So then if we evaluate it, we can pull this constant out, and that would be 0.5 times 10 to the minus 4th. And then you've got a negative there, and you're going to plug in cosine of, you're evaluating at time t, and you're dividing it times 0, but cosine of 0, of course, is going to be 1. So what you're going to end up with is you'll get 1 minus cosine of 10 to the 4th t. Okay, so this constant pulls out, and then we have a negative cosine. So we'll plug in, and we'll get negative this expression here, cosine for the t. But when we plug in 0, we'll say minus cosine of 0, which is 1. It'll be actually, usually it'll be minus minus. So that's why you'll get a positive 1 there. Okay. So therefore, we have what the charge function is. All right. So if we want to just, again, this is what our charge function looks like, Q of t. If we want to go ahead and get the voltage function, we know that V of t is simply the charge function normalized by that capacitance constant C. So in this case, it's 0.1 times its microfarad, so that's 0.1 times 10 to the minus 6 F. So that's the same thing as 10 to the minus 7th farads, okay? So what we should have over here is Q of t divided by 10 to the minus 7. And so you can see what's going to happen here. We will end up dividing this term into this expression for Q of t, and that's just going to change that exponent to what? 10 to the positive 3, right? Minus 4 minus minus will be 7 plus 4. So it changes tremendously to a different order of magnitude there. And you'll have still the 1 minus cosine 10 to the 4th t, okay? Maybe cleaning this up a little bit, moving the decimal a little bit, you would get 500 times 1 minus cosine of 10 to the 4th t, okay? And that again is our voltage function for this capacitance, okay? All right, so if we were to just quickly draw them so we could sort of see the differences, let's just start off and draw initially what the current looks like. The current was given to us, but maybe we'll just sort of sketch it and sketch one of these on top of each other or below each other so we can see the difference. So, we're, for the current function, we're drawing I of t in amps. It'll rise to a half, it'll drop negatively to a negative 1/2, all right? I'm just using this factor right here, okay? And we know we'll get we will get a 0 or a root at pi. We also know it'll keep oscillating through multiples of pi through 0, so it'll look something like this. Okay, I'm just going to use the 1/2 and the negative 1/2 sort of as a boundary. So as it wiggles through there, it'll look something like this. Okay. And I'll just stop there, all right? Now, one thing I'm going to adjust for here is I'm going to adjust the time or the x-axis to be 10 to the minus 4t. Why did I do that? Because you can see what I'm trying to draw. If I draw time at the 10 to the 4th axis, then I can represent these amplitudes very nicely. Otherwise, if time is, I'm just trying to represent you know, a smaller scale representation. So I'm going to take time to be very, very small here, all right? So that when I have pi times 10 to the minus 4, I get sine of pi, which is 0, see? So I'm just going to kind of take out that size of that angle by dropping the scale of time, okay? Just means what I'm inputting is 10 to the minus 4th seconds, not regular seconds, because then this is going to be a huge value, okay? And I don't want to write a huge scale there on the time, okay? So I'm going to keep my time axis kind of small, and I'm going to have to keep it that way for the rest of the graphs, right? Again, it doesn't have to be this way, but it just sort of represents the fact that this is happening relatively quickly, and that's important for capacitance. This is all happening very quickly, all right? So now we're going to sketch the charge. And what we'll do is maybe sketch it below it, just right below it. I'll push this up a little bit and we'll sketch the charge function. Now, the interesting about the charge function is if you look at it very carefully here, this was what it was right here, okay? The maximum value of cosine is going to be 1. The smallest will be -1, but in 0, you'll still get 1 minus 0. This function is never going to be negative. That's what's interesting. It's non-negative there. So we can draw an axis here. We can draw it so that we know that we don't have to dip below the x-axis there. We're going to keep our scale at the same time, 10 to the minus 4 seconds, because of the huge angle is still there. And we're drawing this function right here, okay? And because I'm drawing it at such a tiny scale there, the axis, the y-axis here, again, I'm drawing q of t, the top values I'm looking for will be of the order 100, and then I'll just, for scaling purposes, put 50 here. And you'll see that why that's going to be in just a second, okay? And then what we'll have here at the same, we're going to mark the same time periods, pi and 2 pi, just like we did for the current function. But now this function is going to be triggered by cosine, 1 minus cosine. So I'm going to hash out through the 100 here, which will be our maximum amplitude here. And here's another pi, 3 pi, if we just want to see it there. And this function will look more like this. So it will reach peaks at pi and 3 pi. This is cosine based. So this, we'll sequence through here and we'll come down to 2 pi 0, but then we'll go right back up again, okay? Then come back down again. So this is very different, all right? So this is drawing this function. The input scale is 10 to the minus 4, all right? So again, if I put in pi times 10 to the minus 4, I'll have cosine of pi. Okay, so that's going to be negative. That's going to be okay. Let's just play around. Cosine of 0. Let's just start at 0. Then cosine of 0 is 1, and then of course 1 minus 1 is 0. So regardless of the scale factor, we start at 0. And then when we get to pi, we'll be at cosine of pi times 10 to the minus 4, all right? And this will give us the same thing as cosine of pi, all right? Which would give us a negative, cosine of pi would give us a -1. So we'll have 1 minus 1, which will be a positive 2, all right? And then this will be 2 times the half will give us 1, all right? But we're at the 10 to the minus 4 scale, all right? So maybe we'll just do this calculation so you can see what I'm drawing here is I'm going to draw micro coulombs instead, all right? So again, micro coulombs will be at the scale 10 to the minus C, okay? So when I plug in, we want to illustrate the scaling. This is really important here that you see the scales, that this is over here, we were drawing amps here, but here I'm drawing microcoulombs, right? So what we're getting down here is, if I'll just do this off to the side, if we did Q of pi times 10 to the minus 4 into this function, we would get 0.5 times 10 to the minus 4. You would have 1 minus, and then when this value goes in, we said earlier, this was going to give us cosine of what? Well, the 10 to the 4 times 10 to the minus 4 goes out. Then we'll get cosine of pi, which is -1, okay? And what this value would be then is 2 times 1/2 times 10 to the minus 4, okay? And so that would be 10 to the minus 4. But I'd like to, if I'm going to use a scale where I'd like to see larger values here, because if I left this alone, then I'm going to have to draw this peak at 10 to the minus 4. So what I'm going to do is I'm going to scale by micro coulombs, right, which is 10 to the minus 6, and that gives me 10 squared, or 100, okay? So 100 micro coulombs is equal to 10 to the minus, so what we're saying is 100 coulombs is equal to 10 to the minus 4 coulombs, okay? That's all I'm saying. So, either you could represent this as coulombs and you get tiny values here, but sometimes because we're looking at scales of this order, microcoulombs is very common here, it's nice to see it sort of represent a nice big whole numbers there, right? And then of course, the voltage function is going to look exactly the same at a different scale. And its scale is indicated here, right? Completely different scale now, but we'll go ahead and keep the time dimension the same. So in all your graphs, make sure you keep them the same so you can compare. Things are happening very quickly here in the world of capacitance. So we're looking at very short time passage here. And this time we're drawing the regular voltage at V of t. So the only thing that's scaling is very small coulombs generating voltage of this order. So again, you'll have pi, you'll have 0 at 2 pi, and you'll have the 3 pi and so forth. But the scale now will be huge. This will be 1,000, this will be 500, and you'll see why in just a second. Scaling through there. Okay, so again, the V of t is just Q of t divided by 10 to the minus 7, and we got this function right here, all right? So again, when I plug in 10 to the minus 4th pi, what's gonna happen here? You're gonna get the 10 to the 4th, 10 to the minus 4th go out. You'll have pi. Cosine of pi is -1. 1 minus 1 is 2. 2 times 500 is 1,000, okay? So the curves are exactly the same, but the scales are different, okay? So there's your voltage. So the voltage and the charge, because for capacitance, remember, Q equals C times V. So they should have basically the same shape, they're just scaled differently. Your 1,000 volts is corresponding to 100 microcoulombs, okay? Keep that in mind. See the huge difference in scale of the capacitance values versus the voltage, okay? Very, very different, but the shapes are exactly the same, just completely different scale. And that's because of the typical capacitance values in farads that you're getting. They tend to be very, very, very small, okay? So let's move on to stored energy. So this is an illustration of how you would integrate to get the charge, from the charge, get the voltage. So you have all the representations and changing through time for that capacitance. And then now you're going to look at the energy stored through the power. We already know what power is. Here at the bottom of page 84, power is just voltage times current, right? So if we know that these change with time, all we're going to do is use the fact that, well, in the capacitance world, current is always C times the rate of change of the voltage, okay? The constant times the derivative of voltage with respect to time. So if you just plug this in for the current right there, what the power formula is going to be in this case is C times the voltage times its derivative, okay? All right? If we suppose that the initial voltage is 0, then it wipes out the power, so the initial stored energy is 0. So if you don't have any voltage, you're not going to have any stored energy to starting with, okay? So the corresponding capacitor is, we say, unchanged. Now, suppose the voltage changes from 0 to some specified value by this function past initial time. Well, as the voltage increases, energy is delivered to the capacitor and stored in the electric field between the plates. So to get the power for that, then you're going to have to integrate that power. We've done this before. So to get your stored energy, you're going to have to integrate power from the initial period up through any particular time t. And then again, if we substitute what the formula is for power, then what we'll end up getting is we can quickly change variables here if we change and integrate with respect to V rather than T, or you could almost say that these differentials will divide out, so to speak. And what you've got is you can switch to this integral. You will integrate from 0 to V of T, CV dV. And then if you do that calculation, we just came up with a wonderful formula that the stored energy is this integral, pull the constant out, raise that to the square divided by 2, there you go, okay? So this is a wonderful formula. The stored energy in your capacitors is always the square of your voltage divided by 2 times C. So we don't have to integrate anymore for this. That's the direct formula we can use. We've derived it. That's how you determine how much energy is stored in the capacitor. How much voltage are you generating from that initial time point up to some specific time t, okay? So let's look at that and apply it. And notice before we do that, let's look at a relationship on the top of page 85. So we just derived this as the stored energy formula for capacitance, okay? Substituting variables, in other words, we could rewrite this formula in terms of the relationship between Q and, remember, Q is C, or we could say Q of T is the same thing as C times V of T, right? And so in that particular case, right, if we solved for V of T, we'd have Q of T over C. And so if we plug that in there, we could show that, well, the energy must be just the product of the voltage times the charge divided by 2. So the half stays there, but V now is Q over C, so the C divides out, right? And one of the V's divides out, okay? And so this is what we're left with, okay? Again, if we're not sure how that happened, we're saying C times V of T squared divided by 2 is the same thing as C times V of T times, we're going to keep one of them, and the other one will get Q of T divided by C all over 2, okay? So we have 2 V of T's, but replace one of them by this formula, so therefore the C's completely divide out. And so we have this formula divided by 2, and we could substitute again to get the V of T out of there and use this function. So you have a couple of options. This is one way to get it. Here's another way to get it. So there's several options, several ways. All of these are equivalent ways to get the stored energy. If you only have the voltage, this would be ideal. If you only had the charge, that would be ideal. And if you have both, you could do this, right? So 3 possible ways you could get the stored energy, right? So let's apply a voltage waveform to a 10 microfarad capacitance and determine current, power, and energy stored between 0 and 5 seconds, okay? So this is example 4, really, really nice example here. You just have to be careful with your graphing and your algebra here to get these. Typically, when you have a waveform like this, you're going to break this into a multi-part function, and that's what we've got to remember. Couple of other things, remember that slope is always rise over run if you're looking at how to analyze a linear graph in terms of the slope. And you can see quickly here, there's a rise from, we're in seconds, from 0 to 1 seconds, it goes to 1,000 volts, holds till 3, and then drops linearly back to 0 at 5 seconds, okay? So the first thing we have to do is be able to write, and this is important because if we get this wrong, all the rest of the formulas are going to be wrong. We have to make sure we're representing that voltage correctly, right? So, so we can think about, all right, we need to represent the slope here. We're going from 0 to 1, and clearly the rise is 1,000 volts over 1 second. So the function is just 1,000 T, right? Volts from between, we'll say, we're not going to look specifically at the values, we're sort of instantaneously, just after 0 and right up to 1, it's 1,000 T, right? One way to always get that, remember, is the point slope formula. If you don't remember that, I'll just write it down here. Again, this was this form, y minus y0 equals the slope times x minus x0, where you've got the slope and a point. Okay, there's your point and there's your slope. So that's always the slope of a line if you have a point and a slope. This case, we knew 1,000 was the slope and 0, 0 is on the line. So that gives us linearly that function. I think you know immediately you have a constant voltage of 1,000 volts between 1 and 2, excuse me, 1 and 3. So we'll write it this way from time between 1 and 3. And this is okay because as it flips on that time, it still stays at 1,000, all right? But it's perfectly okay and sort of typical to write the intervals in this way without inequalities. And then it will flip to decreasing mode. So again, we'd have to think about, well, what's the slope? We'll do this one. This one you have to be careful about. Decreasing slopes can cause some people problems. It's going from 1,000 down to 0, right? So if we're thinking about slopes here, we've got the rise is actually a drop, so it's minus 1,000. I'm trying to write the slope, and the run is 2, correct? Okay. So in this case, the slope is minus 500. Again, the rise is a drop, so it's a negative 1,000 drop over a 2 time unit or 2-second run. And the point, we can use either point here. Let's use the fact that we know that 50 is a point on the curve there from 3 to 5 seconds. So we can write the equation as, let's say, y minus 0, of course, is equal to the slope. I'm just write it this way, I'll put it in a minute, of x, or in this case, t minus 5, okay? Our independent variable is t, not x, so I'm going to change it to t here. So y is equal to minus 500 times t minus 5. And so that's equal to what? If we just play a little game here, let's write it this way, 500, and then flip the signs and get 5 minus t. And that's going to be the function here, 500 times 5 minus t volts from time 3 to 5. Okay. Now, if we're not sure about that, you can check that. If you plug in time 3 here, you get 5 minus 3 is 2 times 500 is 1,000, correct? If you plug in 5 here, you would get 0, which is correct, okay? So you can sort of check real quickly, do I have the pieces of this voltage transform waveform correct, okay? So those are all 3 pieces. And so the next chart, the next thing we want to do is produce the current, right? All right, because the current is going to be based on how these change with respect to time, all right? And so we're going to do that then on the next page, 86, 87, and on page 86, we're going to draw each of the remaining curves, all right? And maybe just to be clear, I'll write the voltage function as we flip over so we don't have to keep flipping pages. So off to the side over here, I'm going to write our voltage function that we just determined. So we have it available. It was 1,000 t volts from 0 less than t less than 1. And then it was constant 1,000 volts between time 1 and 3. And then it was 500 times 5 minus t volts from 3 to 5. Okay, so that's just to keep it over there for us. Now you just apply your formulas. In the case of capacitance, current is always that C constant times the rate of change of the voltage, so that derivative, okay? So let's keep in mind what the constant C is. If you go back to the problem, if we go back and look at it, it was a 10 microfarad capacitance. And just so we understand in terms of powers of 10, that's 10 times 10 to the minus 6 farads. So that's really just 10 to the minus 5 farads, okay? Right? So what we're doing is we're going to multiply this value times the derivative of those, all right? So let's go ahead and do that. And these derivatives should be pretty straightforward. This is a linear function, right? And so when you multiply, when you take the derivative of this term, 1,000t, you're just going to get 1,000 back, which is 10 cubed, right? So, and then this is going to get multiplied by this 10 to the minus 5 power right here, okay? So what I'm going to do is I'm going to write this as 10 times 10 to the minus 3rd amps. In other words, I'm going to make a scale change and give it in terms of milliamps, just so I can use larger values, okay, instead of tiny values. Nothing wrong with that. So now that would be equivalent, right? That's 10 to the minus 2 amps, but I'm going to represent it as 10 milliamps, okay? Again, just to make sure we understand, the derivative would have been 1,000, which is 10 cubed, times the 10 to the minus 5, that's what the C is. That would have given us 10 to the minus 2, but I'm going to write that as 10 times 10 to the minus 3 because I'm making a scale change, right? Derivative of a constant is 0, so that doesn't really matter. This is going to be 0 amps, period, no matter whether it's milliamps or not, and so that's easy. And then the last one's a little bit more complicated because you've got this constant. You're going to have the derivative is going to be 500 times negative 1, right? So you're going to get minus 500 times 10 to the minus 5, okay? And again, I'd like to write this in terms of milliamps. So if I want to write it in milliamps, I've got to have this factor, something times 10 to the minus 3, right? So this over here is going to be minus 5 times 10 squared times 10 to the minus 5. So that's going to be minus 5 times 10 to the minus 3. So I'd have a minus 5 here. And that's for time between 3 and 5 seconds, okay? Right? So that allows me now to draw my curve. Obviously, current flips in sign, so it allows me to draw a curve like this, where I have my current, but my scale will be milliamps, so that I can draw just 10 and not really tiny powers of small powers of 10. This is 0, and this goes down to minus 5. So I hope you can understand why sometimes this is difficult for people who are not used to doing different scales, but it allows a human to interpret this so much easier, all right? Because we can deal with integer values very well and just say 10 milliamps instead of 10 to the minus 3 amps, okay? So this was 1 time unit, and then we had a switch at 3, and then we had coming back to 0, whoops, at 5, so we're right there, okay? And so what we're having here is 10 up here, it's constant, 10 milliamps up till time 1, then it goes to 0, and then it flips down to minus 5 milliamps through time unit 5, okay? So this is, I'll kind of bolded face here, this is the current through the capacitance. 10, 1 second, flips, nothing, flips, and then comes back, okay? Right? So very staircased kind of behavior of current, but the important thing is pay attention to scale, right? It may be that when we're solving problems, it doesn't matter. And then of course you'd be free to represent this in regular amps. But if it's necessary for the human perspective, or the user or the client desires it in a particular measure, then you need to make sure you're providing a scale that makes sense to them, okay? In this case, I've chosen that I'd like to keep it with very nice integer values, and then I need to change my scale to milliamps. Let's go ahead and write the power function. Well, we know that the power function, a couple of different ways to write it. We showed the formulas before, but this is just the easiest, right? Voltage times current. So we take the product of the voltage times the current. And so the three-way function here that you'll get is you need to take the voltage function here and multiply it by this current function that we have there, each 3 parts, okay? So let's think about what happens and leave these at these scales. So I drew them on milliamps, but I'm leaving everything in their regular amperes and voltage so I can see what's gonna happen when I multiply. When you take 1,000 T and multiply it by 10 to the minus 3 times 10, I hope you'd see that, well, that's just gonna give you 10 T watts. And that'll be between 0 and 1. Again, 1,000 T times this term right there, 10 T. Then you're still going to have 0 watts between time 1 and 3 because you have no current. And then finally, you have to take this function and scale it by that value, right? And what's going to happen there is the negatives are going to cause a little bit of sign change there. 500 is going to be multiplied by this very small value there, and you'd end up with 2.5 times T to minus 5W from 3 to 5. And you can check that. It's not too difficult because that's 10 squared, and that's going to be multiplied by 10 to the minus 3. So that's 1/10, right? And then you're taking 5, so that's gonna be halving that value out, right? So you're going to take a half of 5, and you're going to get 2.5 there, right? Which is really completely different scale now in terms of watts, okay? So now we can draw this nice, we've got them, and we can now draw the power curve. And in this case, we can go positive and negative, all right? And that's very interesting because you remember with the resistance, while I'm drawing this, remember with the resistance, what is the power always? That's right. The power is always positive for resistance, not here. So in a capacitance, your power is going to flip. It's going to change, okay? You're going to store energy and then you're going to release it. And that's controlled by how you change the voltage. If you increase the voltage, you're storing energy. Once you start decreasing the voltage, you're letting it out. You're releasing the energy to other parts of the circuit, okay? That's what's beautiful about these designs with capacitance, okay? So let's scale it up for our time. 1, 3, again. These were all seconds. I didn't mention that up here. So this is all seconds, okay? And so we're representing power, and this is all in watts, okay? And so what's going to happen between 0 and 1, it's a linear function. It's going to peak up here at 10. So we'll just kind of scale up here. You're going to be at 10. So it's going to be linear up to 10. It's times 0. And then what happens? Beyond 1 second, it goes to 0. So it comes straight down and you have nothing. So this is what power, so that's a power spike. This is typical in power curves. You get a spike, hold, and then what happens here? You got a drop, okay? So when you're at time 3, you're gonna get 3 minus 5, which is -2. So this will come down to -5. So I'm gonna go about halfway down here. This is -5. So you're gonna drop the -5, and then it's linear, so it's gonna work its way all the way back to 5, because when you're at 5, again, you're back to 0. So see the behavior, sawtooth. It's a very sawtooth behavior here, okay? So positive spike, flat, negative spike. So this is very informative here of what's happening. With this spike, just to annotate the graph so we understand what's happening, this is where energy is delivered. So that's energy delivered to the capacitor. So that, again, you're ramping up the voltage. You ramp up the voltage, you get current. So it's cool to see these graphs together. Although I don't have the voltage in front of me here. You ramp it up positively, linearly with a voltage increase. You generate current. Energy is then delivered to the capacitance, right? And then you hold the voltage constant. When you hold the voltage constant, no more current. So energy is no longer delivered, nothing, it's just stored. It's that energy that you accumulated is now stored. And then when you drop the voltage, you get negative current, polarity switched, and then the energy is delivered, or in this case, we'll say the energy flows out of the capacitance. Back to the rest of the network. So that's very important. Let me write this again, rest of the circuit. Voltage increase linearly gets you constant current, allows energy to be delivered, get a spike in power. You stop changing the voltage. So this is not 0 voltage, keep in mind. It's just constant. The derivative is 0. That's what everything, it's all about the rate of change of the voltage for capacitance. And then when that rate of change drops and goes negative, you'll go negative current, and therefore you will generate a release of the energy, okay? That you've stored it and you need it somewhere else to power something else up, okay? And finally, let's just write the energy stored. So just sort of illustrate all 3 together. Again, remember the options. There's a couple of options that we can use to get the energy stored, right? Just so we write them out. One option was the capacitance times the square of the voltage divided by 2, or you could take the voltage times the charge and divide that by 2, or you could take the square of the charge and divide it by twice the constant C. You have many choices there. I typically don't want to involve 2 of them. I think the original voltage curve is just fine. So, and another reason why it might be good is if you made an error with these 2, this at least could be independently correct, all right? So, because this was given to you, all right? So let's just write what the energy stored is in terms of the voltage function. It was up here, maybe just so we can see it all together. We'll write it again one more time. V of t is 1000 t, 1000, these are all volts, and 500 times 5 minus t volts, and then all the appropriate time intervals, 3 less than 5, and of course C is 10 to the minus 5 farads, okay? So now here's our formula. What is the storage energy? We're looking at joules here. So what will we get? So if you square this function, you're going to get t squared. So we're going to get a quadratic, all right? So let's just do this off on the side. What's going to happen? So you've got 10 cubed t, and you're going to square it, correct? And then you're going to divide by 2, and you're going to multiply by 10 to the minus 5, okay? So let's think about what happens there. So you'll have 10 to the minus 5. When you take 10 cubed and square it, you just multiply, right? So you're going to get 10 to the 5th times 10 to the 6th t squared, all divided by 2, right? And so that's going to leave 10 to the minus 5th times 10 to the 6th. That's going to leave 10. 10 divided by 2 is 5. So you're just going to get 5t squared joules, okay? So I wanted you to make sure you could see how you have to be careful with these units, all right? The next one, what will happen here? Well, it's just constant. So you've got 10 cubed, and you're going to square it again, multiply by 10 to the minus 5th, which is C, and divide by 2, and that's just going to give you 5 joules, right? Between 1 and 3 seconds. And then finally, for the last case, this function, now you have to be a little careful when you square it, right? So you're going to have 500 times 5 minus t, quantity squared, push this out. That's going to be multiplied by 10 to the minus 5th, and you're going to divide by 2, okay? Right? Couple of options here. For purposes of graphing, I probably leave this term that's going to be squared alone, all right? Because it's perfectly easy to plug something in. Versus if you factor all that out, then you've got a lot of terms you have to add up. So typically you don't want to do that. You want to kind of keep it simple to substitute for. Let's just play with these constants. And so this would be the same thing as 10 to the minus 5 times, what are you going to get? You're going to get 5 squared, and you're going to get 100 squared. You're going to get 10 to the 4th, correct? I'm squaring both of those, and then that'll be multiplied by 5 times t squared. So yeah, I'm just doing 500 squared, but I'm just kind of breaking the pieces there so I can see how to get the coefficient out. And then that has to all be divided by 2, okay? Well, let's see what's going to happen. You're going to end up with 10 to the minus 5 times 10 to the 4. So that's going to give you 10 to the minus 1, which is 1/10. So you're going to get 1 over 10 times 25, right? Divided by 2. And all that is times 5 minus t squared. So what that is that's 1/10 over, you could say that's just taking 1/10 of that. So you're taking 2.5 divided by 2, and all that's going to be is 1.25 times 5 minus t squared. And if you need a calculator, that's fine, okay? But again, you're taking 1/10 times 25 divided by 2. So that gives us this function, 1.25 times 5 minus t squared. And these are all joules, okay? So the energy now is either a constant or it's quadratic, which is interesting, all right? So let's draw, the scale is joules. Noticing again, as we've seen before, joules will never be negative. So in this case, there's no need to worry about the negative y-axis there. We're still working in seconds. we're still looking at what happens at 1 and 3 and then 5, and we are drawing energy, which is in joules, okay? Again, I'll put the other graph in front of it because up above, of course, is our power in watts. And so what happens here is you're going to get a quadratic that's going to run from 0 to 1, and it'll hit 5. So you're going to peak at 5 joules here. So we'll sketch this across here. Since it's quadratic, there's the data point, kind of make it look quadratic. And then it is constant, so it's kind of like a little volcano. It's constant at 3, and then it's got to make its way down as another quadratic, like that. Again, if I plug in 3 there, I get 5 minus 2, 5 minus 3, which is 2. Squaring it is 4, and then when I multiply out, I would get 5 again. Okay. And of course, when you plug in 5, you get 0. So you see this nice little kind of volcano kind of structure here. So this is just saying the joules will ramp up very quickly, they'll hold constant, and then as the energy is dissipated, you'll drop to nothing. So the capacitance eventually has nothing stored in it. You ramp up with the voltage increase, you hold the voltage constant, just hold it for a while, and then release it at a particular time, okay? So the minute, the length of time you hold it just depends on the effect that you want to have in terms of making that energy through time available to the rest of the circuit, okay? If it needs to be faster, then this has got the holding the voltage constant has to be a shorter time interval, okay? Right. So that's a great illustration of you need to be able to draw or at least analyze all of these kinds of curves depending upon how the initial voltage waveform is given to you. And then we'll talk about relationships between capacitance and the overall circuit design in the next sections.